Yeah. Today, first of all, good afternoon and welcome to our third week as well as fourth week discussion of the for NPTEL program for the course Electrical Machines 2. So the last week, you students have raised the concern that we are 1 week lagging based on the assignment submission deadlines. So yeah, I have talked with the coordinators and they positively.
सर आप म्यूट पे बोल रहे हैं.
Okay. Yeah. Thank you, Shahid. Thank you. Once again, I was just saying good evening and welcome to our third week as well as fourth week discussion for our NPTEL program on Electrical Machines 2 course. As I was saying, the last week some of your students have raised the concern that we are 1 week lagging on the assignment submission deadline dates. So I have put that point with the coordinator and they have responded positively. And from this week onwards, we will be discussing the assignment which you are due tomorrow. So I'm sure you are due for assignment 4 tomorrow. So yeah, we will be discussing the week 4 content and also since we have missed the week 3 content last week, once we discuss the week 4 content, towards the end, we will also discuss some points and some numericals which are related to week 3. And whatever we have discussed in this particular 2 hours of session, the topics which are missed in this session which are useful for assignments submission that will be discussed in the evening session which is from 7 to 9 I presume. Yeah. My fellow TA will discuss the rest of the topics in that. So today we will be discussing week 4 content as a main priority, and towards the end of our lecture we will also discuss the week 3 content. So yeah, let's let's move forward. So this the week 3 and week 4 are having similar kind of content altogether. It's based on winding in a machine and what kind of terminology, what are the different factors, and what are the different kinds of uh, uh, connections, and how a winding table is made for a three-phase balanced winding for different kinds of poles law combination. So yeah, both 3 and 4 weeks of content covers these basic topics in it. Before starting our week 4 content, I just want to tell this point. So in a machine, there will be coils and windings are distributed. There might be concentrated winding. But before going into that, we need to understand some terminology in a machine. There are some factors or some terms which we should be aware of before directly solving some problems. For example, what is a distribution factor? What is a pitch factor? And what is coil span, slot pitch, slots per pole, everything. This kind of basic terminology is very important to understand. So to solve the problems or to understand even how machine winding works. So yeah, with that in mind, we will start today's discussion with basic terminology in windings. And first, we will be discussing about the distribution factor as well as pitch factor, which the product of which is nothing but the winding factor. So first, we will see the distribution factor. So it is denoted by KD. K with a subscript of D. D denotes distribution. Later we will be seeing that the pitch factor, K with a subscript P, where P denotes the pitch factor. And these are simple formulas. You can also remember them, but it's useful for you to remember these formulas to directly solve the problems. But before remembering that, it is very important to understand how that problem came and that particular formula came and how it is being calculated. So that's very important. There is a theory behind this formula, how this formula came into picture. So that's very important to understand. So that's the purpose of today's discussion of this terminology of distribution factor and pitch factor. Now, yeah, the first we will be starting with the distribution factor, and I want to tell in a machine, coils will be there, and the coils will be distributed or coils will be concentrated kind. But for many reasons, we don't actually prefer concentrated winding. Yeah, in the weak content, professor also talked about this, why constant winding is not good. I will also repeat those points. So because concentrated winding means, the name itself says, many number of turns will be accommodated in only one pair of slot. If this is a slot, many coils will be placed in this slot itself. So it is like concentrated in that particular slot. So if you are placing many coils in that particular slots, there will be a rest of the place in the machine, rest of the slots will be remain unaccommodated, unused. So it's a waste of space there. So that's one of the reason which we don't go for concentrated winding. And another reason is, there is a limit to place. There is a restriction on number of turns you can put in a slot. There is a limit, so it can't be any number of turns. So uh, it is suggested to nicely distribute the winding and place slots in a distributed manner. One slot after one slot, one slot after another slot. So this kind we will be utilizing the entire machine space, machine slots space, and also we will have a nice distributed winding. So this is some of the reasons why we don't go for concentrated winding. Yeah, but there is a catch here. Because of this distributed kind of winding, there rises some kind of difference in the voltage induced in each coil. So why that difference? We will look into it. So yeah, this is the kind of discussion we will be going towards now. So what exactly is a distribution factor and why it comes into the picture? So yeah, now for example, let's take say 30, you have 30 turns and you want to distribute in 3 coils. So my ideal distribution would be 10 turns in coil 1, 10 turns in coil 2, 10 turns in coil 3. Let's say suppose I have 3 coils and I have distributed my 30 turns in that kind of combination. So let's say I have, for example only, just to make understand. So let's say there's a machine, one one dash is one coil. One, this is coil number one. One dash. So one means going path, and one dash will be the return path. So this is the convention we are following now. Later we will also change this convention, but right now it's simple. It's simple. There's no need to complicate things now. So let's say we have a coil one. It is one dash, and coil two is here, two dash, and let's say coil three here. It's a example only. It's fine. Wherever you place the coil, whatever it is, it's fine. So one dash, two dash, three dash. I have placed my windings like this, and in each coil one dash I have placed 10 turns, two dash 10 turns, and three dash 10 turns. Now I am interested to calculate the EMF induced in each coil. Like what is the total induced EMF that is induced in total, three of the coils. Let's say, yeah. So yeah, E11 dash. Let's say E11 dash is the EMF induced in the coil number one, and similarly E22 dash is the EMF induced in coil two, and these are the magnitudes. E33 dash is the EMF induced in the coil 3. Now I want to find the total amount of induced EMF. It's just a algebraic sum of these three, and in concentrated winding there won't be three different slots here. In the single slot we will insert the three. So that in that case also we will find induced EMF. In this case, distributed winding, we will find induced EMF, and we will see what's the difference it will arise. So that will give us some idea on what we are interested in discussing today. Now, let's say we know these three. Since see, we have taken equal number of slots, equal number of coils in each coil, equal number of turns in each coil. So 10, 10, 10. So we are assuming that the magnitude of these three induced EMF voltages is equal. Uh, I mean equal magnitude. So let's say now we want to calculate the total EMF that is distributed across these three. Uh, so yeah, this one is slot number coil number one, coil number two, coil number three. Now this is the angle between these two slots, which we call as a beta, that is slot pitch. Now this is 2 and this is 3 and this one is also beta. So angle between each slot we term it as a slot pitch. So we gave the particular letter we denote the slot pitch is with a beta. So that's important. We will see later onwards how it is important to calculate different problems. Now let's say I'm interested to calculate the resultant. So I know this E11, E22 and E33 dash individually. The reason which I specified beta is, let's say 111 is in, let's say this is in this phase, and my second coil will see the same amount of magnetic field seen by the first coil, but after a lagging of beta. So once first coil, let's say the machine is like this, my field is moving. First, my coil 1 will see the magnetic field, and after beta degree displacement, my second one will see. So there is a beta degree lag between second coil, the flux seen by the second coil, magnetic field seen in the second coil with respect to the first coil. So that's what I'm trying to represent here. Let's say this one is E11 dash with an angle displacement of beta. Let's say this is beta. I will have my E22 dash. So that's what I wanted to tell. Again, if this is one, and with respect to this one, there will be another beta displacement where we will be having E33 dash. So yeah, that's the reason which I brought up the discussion of beta here. Now, yeah, let's draw it in a clear manner here. Now, okay, this is E11 dash. So this is this axis of that E11 dash, and with the displacement of beta, you will have E22 dash, and with the displacement of this is angle, okay, and this is again beta, you will have E33 dash. Yeah. Now we are interested in the resultant magnitude, that is this one. Yeah. So this one is what? E13 dash. This is the resultant that we are interested in. Now, this kind of a distribution will also be present in the concentrated winding. So this is for a distributed winding. But it's simple. For a concentrated winding, there won't be any beta because all the coils are all the turns are placed in single slot. Now we will see the phasor. This is the phasor diagram. Phasor diagram for distributed winding. Now let's see for a concentrated winding. There won't be any angular displacement here. Now let's say this is you have to keep in mind that these are all of equal length because equal distribution will be there. These three are of same length. Now if you see the concentrated winding E11 dash, and this will be in same phase because all are the same phase. We call these phasors as co-phasors. E22 dash and E33 dash. This is the starting point, and moreover, these are of same length. Okay. Now, in this case, if you see the algebraic sum in concentrated winding, the algebraic sum of these three phases magnitude will be more compared to this case because here there is an angular displacement, and the algebraic sum, the resultant here, will be of less magnitude compared to these three here. Here simply we are taking the maximum magnitude and we are taking algebraic sum, but here there will be the resultant will be less than the total voltage that we can able to get in concentrated winding. So that's a little bit of disadvantage which comes along with the distributed kind of winding. So the total resultant magnitude will be less. But what is that factor by which it is less? That is what we are interested in. So our problem statement comes here. The discussion point will be the question. The main question is, let's say if we connect three coils in concentrated way and also in the distributed way. Now, what is the ratio of the resultant voltages that are induced in these two kinds of winding? So, if we take the ratio of it, that that will actually give the factor by which the voltage is being reduced. So, that particular factor is called distribution factor KD. I think now you got the point. Why we are talking about this kind of distributed factor? Because whenever we connect the winding in distributed factor, our voltage will be reduced by a factor. So that factor comes when you take the ratio between these two. So that is called the distribution factor. Now let's see quickly here. Case A, when coils are distributed. Okay, the coils are connected in series only. So I'm just drawing the circuit connection, not the phasor connection. Let's say this coil 1 is in series with coil 2 is in series with coil 3. So this is 1 1 dash, 2 2 dash, 3 3 dash, plus minus plus minus. It's in series, no? That's right. Now we know that in case of distributed, angle between two consecutive slots will be beta, that we know. How do we calculate the beta? We have to keep in mind that it is beta electrical. I will write beta electrical. Now, how to calculate? Let's say a quick example I will give you. So let's say there are 36 slots in a machine, and now beta mechanical. Mechanical is just how you look at a machine. So every machine has 360 degrees. That is mechanically you can see it. Now 36 slots are divided across 360 degrees. Now the beta mechanical will be 360 by uh, uh, 36 slots. Now, yeah, total 360 is divided across 36. It is 10 degrees. That is beta mechanical. Now, what is electrical? To get electrical angle, we have to multiply the mechanical angle with the pole pairs. Then you will get the electrical. So that is what electrical beta means. That is the angle between two consecutive slots. Now, okay. And we also know that magnitude of 1 1 dash is equal to magnitude of 2 2 dash is equal to magnitude of voltage induced in third coil, that is E33 dash. Yeah. So let's say that is equals to E. Okay. Yeah. So this is what we are trying to just put it to. Yeah. Maybe we can just give it a value here. That is E. Now let me draw the phasor. Let's say this is my starting point A, and this is my E11 dash. And yeah, we know that there will be a beta displacement. We will have the EMF induced in the second coil. This will be E22 dash, and with beta displacement E33 dash. So yeah, this angle is always beta, and this angle is always beta. Now we know these three are equal length, that is E, right? Yeah. Now I'm trying to find the resultant. Okay. I'm trying to find the resultant. Okay. Yeah. So let's say this is A and B, C, D. I am interested to find AD magnitude. Magnitude AD. So that's the point of interest in this distributed kind of finding. Right. Now, how to find AD? When I know the individual phasors and individual angles between it, and how to find, I would like to calculate the value of E13 dash. So this AD is nothing but E13 dash. Yeah. So this is what we're interested in. Now, if you see this particular this is like a polygon of sides, and you can try to visualize it that these are like a sides of polygon that can be circumscribed by a circle. Now I'm just trying to this will be at a point. Yeah. So yeah, this will be this point will be like this anyway. Yeah. This is like a circle circumscribed like here. Somewhere here we will have a center O. So this is circle, and we will have a circle O, center O here. Now I will use some geometry or circle properties to find the length of the AD. Uh, let me take some other color. Yeah. Now let's draw a perpendicular OM onto the this resultant from O. This is M. So this is a perpendicular we have drawn from center of the circle OM, and yeah, for example, so this is nothing but the radius. If you see AD is a radius R, right? So so sorry, AD is not radius. Okay, what happened? Mm, okay, sorry. Yeah. So from the center, we know what the radius is. OD and OC and OB and OA. These are radius of the circle. R. Let's say we're denoting the radius of circle by R. Now, then E13 dash, that is the resultant which we are interested in, we can calculate that in terms of radius of the circle. So, let's say how we can find it. Now, take this triangle AOM. So that is nothing but these three AOM. This triangle, if you take, we know that each angle this angle is beta, this angle is beta, and yeah, this angle is beta. Now if you see, if you AOM, right? Now this total angle will be 3 beta, and this angle which we are interested, this will be 3 beta, half of that 3 beta by 2. In this triangle AOM, angle AOM is 3 beta by 2. So it's divided by half of the total angle, that is 3 beta. We have drawn a perpendicular, and that is divided into half. That is angle AOM is 3 beta by 2. Now can someone tell me what is the magnitude of AM here? AM is this part. This part. In this triangle, we know this angle and we know the hypotenuse, that is radius. Now we have to find the opposite side. So based on trigonometry relation, AM is nothing but R sine 3 beta by 2. Okay. Now this is what AM is. AM is half of the resultant, right? If we want AD, see AD is what we need. AD is equals to 2 times of AM. This is the half side, and yeah. So AD will be 2R sine 3 beta by 2. Yeah. Now we have found the magnitude of voltages in case of distributed winding. Now we will see. We already saw that in case of concentrated winding, if you see this concentrated winding, the total sum is nothing but E13 dash in this case is equal to simple addition. It's in the same phase. There is no beta here. So it's nothing but 3E. Since we took that magnitude will be equal to E. In case of concentrated, it will be 3E. But in terms of, in case of distributed, it will be 2R sine 3 beta by 2. Now, let's take ratio of this. That thing is nothing but the KD which we are interested in. Now, the KD will be resultant voltage when coils are distributed divided by resultant voltage when coils are concentrated. Okay, now okay, so now KD is nothing but the numerator. In case of distributed, what is the ratio we got? What is the value we got for the resultant? 2R sine 3 beta by 2. 2R sine 3 beta by 2. And the resultant voltage in terms of concentrated is nothing but 3E. Okay, this is the ratio. But if you see, it is in terms of R and E. We need a particular value, right? So let's try to convert the R term into E as well. So let's go back to diagram. And in this diagram, if you see, I want to calculate R in terms of E. So what I will do, I'll just draw a perpendicular like this. That is ON. I am drawing I have drawn a perpendicular ON, and this OND triangle. If you look at this particular right angle triangle OND, what is ND here? So I know the hypotenuse, that is radius, and I know this angle. What is this angle? This total angle is beta, and this angle will be beta by 2, right? And my ND will be equal to R sine beta by 2. Okay, but I am interested in this whole CD. What CD? CD will be 2 times of ND, right? So it's 2R sine beta by 2. Why I took CD? Because I know the magnitude of CD, that is nothing but E, right? Now 2R sine beta is equals to E. Now let's take this and put it here. Now we know that E is equals to 2R sine beta by 2. Now substitute it here. 2R sine 3 beta by 2 divided by E is 2R sine beta by 2. Now 2R gets cancelled. KD will be sine 3 beta by 2 by 3 sine beta by 2. So this is the ratio which we call as distribution factor, and this is the factor by which our resultant magnitude of voltage will reduce if we go for distributed kind of winding in place of concentrated winding. So this is what we are trying to say here. Now the three number which we are seeing here is because we took three coils. That's why we got three coils. Let's say if there are m coils which are distributed, number of coils that are distributed. Now the KD will be sine m beta by 2, m sine beta by 2. So the KD will, this is the generalized formula if there are m number of coils that are distributed, and the beta here will be the angle between two consecutive slots. That's a slot pitch. So yeah, so uh, this is about the distribution factor KET. Now we will look into the next factor, which is a simple factor, that is pitch factor. I told you that pitch factor is denoted by Kp, K with a subscript P, where P denotes the pitch factor. Now we will also quickly see what is actually pitch factor, and when does it come into picture, and what is the value of pitch factor, and what is the significance of this particular pitch factor. Now we are talking about, let's say we have coil 1 dash. 1 will be the going path and 1 dash will be its return path. That's what we are talking about. Now let's say 1, this is what I'm just trying to, many number of turns are there. So 1, this is 1 dash coil, return path is 1 dash, and this is 1 dash, and let's say this is 0 0. That's the overhang part, backside side of the coil. Now in this coil I'm saying that this 1 0, let's say this 1 0 is under north pole or south pole. We will try to place the other end of the coil under the opposite pole. So if it is on north pole, we will try to place our next return part of the coil under the south pole. The reason behind it, now these are under the both opposite polarity of the maximum strength. Now then the resultant voltage which I will get will be the maximum. So that's why the reason behind placing the one end and the other end in two different poles. But we know that the north and south poles are displaced by 180 degrees. So that's how the poles are distributed. So yeah, I mean to say that the span between each coil will be 180 degrees electrical. Now that is what we call as coil span. The span till which my coil has spread. So this is the coil span. A coil span should be 180 degrees. So then only we will get maximum voltage as an output. So to get a maximum voltage and output, we will always place the two ends, that is going end and coming back end, under the different poles. If it is north pole, the return end should be under the south pole. So this is the 180 degrees coil span. So yeah, for example, in terms of, if you want to, for example, in terms of calculations, if you want to see, let's say slots per pole. Yeah. Let's say we have slots per pole number is 6. So for each pole, let's say under the north pole, this is let's say under this is south pole. So under north pole we have 6 slots, and south pole we have 6 slots. And now the displacement between each pole is 180 degrees. So each pole will take 180 electrical degrees of span. Now, so this, now the beta we will take it as 180 by 6. This is nothing but 30. So each slot will have a 30 degrees of slot pitch. uh, 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 I mean to say is, so there are six slots in it under each pole. Now, when I place, let's say coil one, this is one dash now. If I place coil one in slot one, now I will place coil one dash. I will place in slot 7. How? Because 1 to 7 there is a 6 slots. So I have covered entire pole here. After 6 slots, I will place my 1 dash here. If I place 1 here, my 1 dash I will place here. So that's how I'm covering 180 degrees electrical and 6 slots. So 1 plus 6. After 6 slots, I will place my return side of the coil. So that I will ensure that my other side of the coil is under the influence of opposite pole, that is south pole. Now, yeah, that's how we got 6 beta is equals to 30. Under each slot per pole, we will first calculate the angle, that is 30 degrees. And if we place our coil in that, if the coil span is 180, if the coil is placed in 1, the return side should be placed in after 180 degrees electrical, that is in 7th slot. Now, there comes a case where we don't place in that kind of fashion. That means I won't cover 180 degree. Let's say this is my case, and 1 0, and this is 1 dash and 0. This time I won't cover coil span of 180. I will just place till 130 only. So there is a 30-degree gap there. So this kind of connection we call it as short pitching. So if you see, there is a 30 degrees of angle is still left, and my coil is not placed under the different poles now. So I have short pitched my connection by a 30 degrees. So I will call this kind of connection as a short pitch winding, and here my short pitch angle is 30. In this kind of connection, I told you already, if it is a full pitched coil, this kind of connection we will call as full pitch, because here the coil span will be 180 degree, and here it is 150 degree. Now, in case of full pitch coil, I told you that we will get the maximum voltage because they are under different poles of reverse polarity, and maximum strength will be there. Now, in this case of short pitched winding, we will get a bit less voltage because we have short pitched by 30 degrees. Now, same, if we take the ratio in these two cases, by what factor the voltage will reduce. So that is called as a pitch factor. So that is the previously we discussed the distribution factor. That is the ratio of the resultant voltages in both distributed and concentrated. Here the ratio will be between the resultant voltages in short pitched divided by the full pitched. So that is what we are interested in. Yeah, this is what we usually observe in the numericals also. They will tell you that the winding is short pitched by one slot, or see here 30 degrees. Now we already saw that 30 degrees, that is for each slot pitch. Now that means that we have placed our coil, instead of 7th one, we have placed in 6th one only. So that means my winding is short pitched by one slot. So that is the terminology we use in the numericals. You have to keep in mind that whenever they say they have short pitched winding by one slot, you can calculate what is the angle difference there. So I will just try to show here. So it means that this kind of angle, we will say this angle as a epsilon. So here the epsilon is short pitch angle, that is 30 degrees. We have short pitched our coil by 30 degrees. Now we are interested in calculating the induced voltage in this case. What is the induced voltage in short pitch kind of winding? First, let's see, in case of full pitch coil condition, what is the induced voltage. Now I know that the angle between these two coils is 180 degree because north and south pole are displaced by 180 degree. let's say this is my 1 1 dash coil, 1 0 dash, and sorry, 1 0 and 1 dash 0. So this is my coil. See here, 1 0 and 1 dash 0. Now, if I know the magnitude of the voltage of 1 0, and the magnitude of 1 dash 0 will be where? Exactly 180 degrees displaced from 1 0, because it is north and south pole in the full pitch. So this is E1 dash 0. Yeah. These two are equal magnitude because similar kind of flux will be seen by both windings. It's just placed in different poles under different poles. Now I want to get total E resultant, that will be E11 dash will be equal to E10. This is minus, right? Minus E1 dash 0. It's like both. Now I will just take the mirror image of this 1 0, that is negative sign. Now I can write this as, let's say this is E10. Now I have to take the negative sign of it. This is minus E1 dash 0, right? Uh, if it is it is 1 dash 0, it is negative. I have taken the negative sign. So the total magnitude is, I am interested in this one. So I already told you that these are a equal magnitude. Now the total resultant will be, if it is E and the magnitude of this one is E and magnitude of this one is E, my total resultant will be resultant induced voltage is equals to 2E. This one plus that this voltage 2E. So this is what I will get in full pitch. It is easy because it's in same 180 degrees out of phase, but in same magnitude. So I will take the minus sign and it will just add it, because I am interested in magnitudes. So the resultant induced voltage in case of full pitch is 2E. Now we will just quickly see in case of short pitch. Short pitch winding. Now, yeah, I have told you. Let's say multiple turns are there, and this is one dash, and I know this is not 180. This is 180 minus epsilon, right? Now this is 1 0, and this is 1 dash 0, and I know if this is my E10, this is this one equal side. Now this is my, previously it is 180 degrees, but now it's not 180, it's less than 180. It will be somewhere around like this. So this will be 180 minus epsilon. You know that.
Sir, 120 degrees, 60 or 90 degrees come in short pitch.
Sorry?
So 120 degrees, 60 degree and 90 degree space angle is come in short pitch
No.
winding.
Yeah. In short pitch winding, they will say that your winding is short pitched by 30 degrees or 60 degrees, or in terms of slots also they will speak. Then we can calculate what is the coil span. There we will get 150 coil span, 120 coil span. Yeah, that we will get in short pitch. Understood, Ranjit? Okay. Yeah, this is E1 dash 0. This is at an angle of 180 minus epsilon. Epsilon is the short pitched angle. Now, yeah, this is also epsilon, because 180 minus epsilon, this is epsilon. So the total will be 180. Now, we are interested to find the resultant. What I will do, I will just modify this. This is E10. This is the one. So this one I know. This is E1 dash 0. and I will take this in phase, right? I will draw a line parallel here. So this is same, nothing but this one only. I have written in this fashion, and this is minus E1 dash 0. It's the same parallel line here, but in a different direction. That's why I took the minus sign. Now I am interested to find the resultant, which is this one, E11 dash. Now I know this angle is 180 minus epsilon, and this is epsilon, and yeah, we know, right, if this is 180 minus epsilon, this will be also 180 minus epsilon. This is 180 minus epsilon, and I also know that these two are equal sides, so that means this is an isosceles triangle. So this is 180 minus epsilon. The sum of the angles in a triangle is 180, and if this is 180 minus epsilon, the sum of these two angles should be epsilon. So then only epsilon plus 180 minus epsilon, that will give you 180 degrees inside a triangle. Now, since it's an isosceles triangle, these two sides are of equal length. This will be epsilon by 2, and this will be epsilon by 2. So yeah, this is the triangle which we are interested in right now. Now in this particular, let's try to draw a perpendicular from here. This is the perpendicular I have drawn from this. Let's give some quickly names. O, this is A and B. So I have drawn a perpendicular here, that is M, O M. If you see, I am interested in AB. That's the resultant. AB is nothing but AM plus BM. Now, can anyone tell me what is AM? If you see AM, this one, I know this angle epsilon by 2. I know this is the hypotenuse. And what is my AM? AM will be E10 cos epsilon by 2. Now, similarly, BM, if you take BM, E1 dash 0 magnitude cos epsilon by 2. So, from these two, we know that magnitude is equals to E, right? Now, AB is nothing but my resultant is equals to AM plus BM. If you add it, it's 2E cos epsilon by 2. So E10 and magnitude, these both are equal. That's why I have added these two. Okay, this is what we get in terms in case of a short pitched winding. Now let's take ratio in both cases. We already calculated for full pitched. What is the full pitched resultant voltage we got? 2E. In short pitched, it's 2E cos epsilon by 2, and in full pitched, it is 2E. So this ratio is nothing but pitch factor. 2E will get cancelled. Now, finally, my pitch factor Kp is equals to cos epsilon by 2. So where epsilon is my short pitched angle. Now, what is even the reason to go for short pitched? I am already telling that if you are going for a short pitch, you won't be getting the maximum induced voltage. Here you can see the factor is reduced by cos epsilon by 2 factor. But still, what is the reason to go for short pitched winding? So this is an important question. Why do we actually need short pitch? Because the reason is whenever there is an input voltage or AC voltage we are giving in or any kind of voltage, harmonics will come along with it. Now we don't want higher order harmonics, lower order harmonics, or some order harmonics present in the voltage. Now the reason behind short pitching a coil by some kind of angle, because when we short pitch by that, let's say some kind of the reason is when we short pitch it, we can able to eliminate some kind of harmonics. If you want to eliminate third order harmonics or fifth order harmonics, we have just we have to calculate the factor for which we can make that harmonics as zero. So I mean, uh, by taking that kind of slot pitch angle, let's say if I want to eliminate third harmonic, I will go for 3 epsilon by 2 short pitch angle. If I eliminate one fifth harmonic, I will go for 5 epsilon by 2 short pitch angle. Then I will calculate the Kp factor and I will equate to 0, and I will know what is the angle of epsilon. Then I can know that if I short pitch by this kind of epsilon, and I can eliminate that harmonic. So that's the reason we go for like, let's say I will just write here K3P, K5P. So this is the pitch factor for third harmonic. If you want to eliminate it, the formula will be cos 3 epsilon by 2 and cos 5 epsilon by 2. Now equate these factor to 0 and find epsilon, and yeah, then you can know if you short pitch by that angle, you can eliminate that particular harmonics. That's the only reason we go for short pitched winding. And yeah, the final closing point for these factors is, now we have seen two different factors, distribution factor and pitch factor. Now in AC machines, these two ratios, Kp and Kd, now if the windings are distributed and short pitched, the voltages will be reduced by a factor which is nothing but a multiplication of these two factors, which I will call as window factor, that is multiplication of Kp and Kd. So this is what we call, sorry, winding factor, K double. So if your coil is both distributed and short pitched, you will get a voltage which is reduced by this particular winding factor. So you just have to multiply the pitch factor and distribution factor, and you can get the factor of winding factor, and you multiply this winding factor with the voltage, resultant voltage, and you can know what is your actual voltage you will get with this kind of winding, which is both distributed and short pitched. So yeah, now with these basics, I think we are ready now to discuss the winding table, or what winding terminology. We are now equipped with all kind of factors, and also slot pitch, coil span, everything. Now I think now it's time we can go for understanding the winding table or winding diagram. But before going that, I will just brief you about a convention I want to tell you, that will be helpful in solving the problems we have. Yeah. So yeah. Sorry. Now let's say we will look into how a three-phase winding looks like. For example, we will take always solving an examples and taking an examples is very much useful. So I will recommend whenever you solve some problems, you go with many numericals and tutorials so that you will get actual understanding. We will look now very clearly what exactly happens in a winding, and it's all based on numbers. If you can understand the logic behind it, it's very easy to draw a winding table or to complete a winding diagram in a machine. Now let's say I have 12 slots and a two pole machine. S denotes the slots and P denotes the poles. Two pole machine and 12 slots machine. And also I am having a full pitch coil now. Let's don't make complicated here. So it's a full pitch coil. That means my coil span. How much is the coil span in full pitch? It is 180 degree. Now what will be the my beta angle between each slot? What is slot per pole? 12 by 2 is equals to 6. Now this will give me beta is equal to 180 divided by this 6, 30 degree. Now this one is the electrical. Now but each slot will have a 30 degrees of slot pitch, electrical degrees. Electrical is very important. You have to always take the electrical beta. Now, let me just try to give a slot here. Let's say I'm trying to 1, 2, 3, 4. The slots: fifth slot, sixth slot, seventh slot, eighth slot, ninth slot, 10th slot, 11th slot, 12 slots. So this is 12. Now after that it will again repeat 1. Here it is. Here it is again 12. Yeah, yeah. Now let's say this is my slot combination and we have two poles that is already there. One is north pole and another one is south pole. Now let's say I am placing. Okay. So you have to mail the coordinator because I am not aware of these problems. You can also raise this point in the discussion forum because we are teaching TAs and this kind of course TAs will be some other one who takes care of registration. You can mail the registration help desk or discussion forum. I'm sure they will reply there. So yeah, I'm saying that let's say this one, I have placed my coil here in one side of the coil in slot 1. So can anyone tell me where should I place my return side? I just explained you. It's very simple.
7.
Yeah, exactly. Can you tell me why it is 7?
1 plus 6, sir, 7.
Yeah, how you got the sixth one? How you got the sixth number?
Because coil is 60 degrees slot pitch. 6, 1, 12 by 2 is 6. That's why we add 1 plus 6.
Yeah,
7.
it means that exactly correct, Ranjit. So if this is the poles, we say slots per pole. Each pole will have 6 slots. Now from here from till 12, I will have a south pole. So if I'm placing one under the north pole, after 6 slots, I will the seventh south pole will start. There I will place my return part of the first one. Now the convention till we followed is 1 dash 2 dash for return path. But now to make it simple, to remember nicely, if it is 1, the return path will be 7 dash. So that's how we will take the convention. So this is a single layer winding. Single layer winding means each slot will have only one coil side. That means that 1 and 7. These two slots are occupied by a single coil, that is coil number 1. Now, if we have 12 slots, you can place only 6 coils in it because each coil, we take 2 slots for both coil sides. Now, let's say in case of double layer winding, what happens? Double layer winding, let's say this is my coil slot 1, and after that, I will have my slot 7. I will have 2 decks here. Now, let's say top coil. This is the going path. This is my coil side 1. I have placed 1 here. My return path I will place at the bottom side. This is 7 dash I will say. So 1 7 dash is my coil 1. And there might be some other coil here which is the return path 1 dash of some other coil. And from 7 some other coil will start, that is 7, that will have some other return path in some other slot. So this is a double layer winding. In double layer winding, uh, if there are 12 slots, I can accommodate 12 coils. So that is very important because in each slot we are able to place 2 coil sides. Now another important formula or simple technique, by seeing it we can say that in case of double layer winding, number of slots is equals to number of coils in case of double layer winding. But in case of single layer winding, in case of single layer, what is the relation? Number of slots is equals to 2 times the number of coils, or you can say number of coils is equals to number of slots by 2. So that's the relation in case of a double layer winding. So I have told you this kind of convention because till now we are following convention of 1 1 dash as a 2 2 dash, but now from now we will have to keep in mind 1 7 dash is coil 1 because the return path is 7, the going path is 1. So yeah, so coming back to our example, now it's a double layer winding. It's not a single layer winding anymore. S is equals to 12, 2 poles, and I am trying to make a three-phase double layer winding. So I will write it double layer winding and full pitch coil. That means epsilon is equals to 0. There is no short pitch here. Now, yeah, I will ask simple questions. Please try to answer it. So, can someone tell me number of coils? How much is the number of coils here?
2,
How much?
2.
2. No.
Yes.
Number of coils.
24.
No. It's double layer winding.
6. I think
Okay.
6.
12, sir.
12. See, if, I just told you. In a double layer winding, number of slots is equals to number of coils. So I asked number of coils. It is equals
12, 12.
right. Correct. It's a 12. Since slots is equals to coils in double layer winding. Now, my second question, number of coils. I know there are total 12 coils. Number of coils per phase. How much is this? How many phases we have? 3 phases.
4.
Right.
Answer 4.
Yeah. So for each phase, let's say I'm having R, Y, B, I will have to place 4 coils. If you understand this one, it will be very simple for you to solve assignment question, which is very simple. I'm telling. You just have to pay attention. Now, one more thing. Yeah. Now I know slots per pole. That is how much? 6 slots per pole. Now, here I have marked it. For each pole, I am having 6 slots. That is clear. Now, this is equals to 180 degrees coil span. Now my beta, how much is beta? Have you calculated beta here? Yeah, beta electrical is 30. 180 divided by 6, that is 30. Okay. Uh, Now I have said that for each pole, for each north pole, I have given 6 slots. So with in that I will divide it. Now north and south. So under North Pole, how many coils are there? 1, 2, 3, 4, 5, 6. And under South Pole, 1, 2, 3, 4, 5, 6. Now the division is clear now. Out of 6 slots for each pole, uh, 6 slots per pole. So 2 for R, and I will give 2 to Y phase and 2 to B phase. That is simple logic. So within 6 slots per pole, this is like a distribution which will give for each phase. Now my question is, R phase, Y phase, and B phase windings are exactly similar. That we know. It's just what is the angle displacement between each phase? Balance 3 phase.
120 degree.
Exactly. So R and Y, they see the same kind of field. It's just that they are displaced 120 degrees in space. Now that is the point which I have to mention here. RYB exactly similar winding but displaced by 120 degrees in space. Now, with this point, next point, I already know inside R. Let's say I started this coil one. The written part is we already discussed. It is 7 dash, right? Now inside R phase, if I start with 1, I will return at 7 dash because it is a full pitched coil and coil span is 180 degree. Okay. Yeah. Now one more important point is per phase. Uh, if you see R phase, within the R phase, number of slots allotted per pole is, if you take north pole individually, within a phase I have allotted 2 coils here. That distribution is already clear. Now we will also calculate that by formula. Slots per pole per phase. Total slots are 12. With 12 slots per pole, we have 6 slots, and per phase we will get 2 slots. So 12 per by 2 by 3. This is it 2 or not? Yeah, it's 2. So that we can see from figure as well. Inside each phase, let's say inside R for north pole, we have two slots. So that is also clear. Now second slot in R phase, that is this one, this particular winding. I'm just taking the R phase and north pole windings, and if it is 1 and 7 dash, this we got. This is because of the coil span. And the second slot, the second coil, what is this return slot number? Can anyone tell what will be the return slot for this coil? It's simple.
8 dash
Yes, 2 8
8.
dash, because sorry, it is because my coil span will won't change. It is a full pitched winding. 180 degrees is my coil span. That means the gap between each coil side will be 6 slots anytime. In any phase, you will take R, Y, B. Under any pole, the coil span will be 180 degree. So if I am placing a coil in slot number X, the return path will always be in the slot where it is X plus 6. That is always there. Now we have completed 1 7 and 2 8. This we completed 1 7 and 2 8 dash. Now sorry, yeah. Now if you see under south pole, we have, see, under north pole these two are done, and under south pole we have two more coils left. Now we have to get to the number in which slot we will place the first coil of this one. Like I am just drawing here. These two are under south. Now what is this number? So to find this number, there is a very simple logic. North pole and south pole. We know that they are 180 degrees displaced. That is the coil span. Our poles are distributed 180 degree. And if uh, uh, north and south pole will be displaced by 180 degree, that we know. And one more thing, within phase, this number, I'll just take another sheet. Yeah, I'm just quickly drawing the coils. This one. So this is under R, this is under Y, and this is under B phase. Now this one we got 1 7 dash, 2 8 dash. And what is this number? And what is this number? So these two are under North Pole and these two are under South Pole. Now if I want to find let's say first we are interested in this one. It is the starting coil in the Y phase. Now we also know RYB from this point number 4. If you see, the coils are displaced by 120 degrees in space. Now we need to find how many slots will account for that 120 degrees. That is simple. 180 degrees means how many slots? 6 slots. That's the coil span. And from that we already got that beta is equals to 30 degrees. So now if I want to calculate how many slots does this is one slot pitch is 30. We already calculated these two values. Now 120 degrees means how many slots? Can anyone tell me how many slots is 120? Simple. 120 by 30. This is beta. This is the phase displacement between two phases. This is 4 slots. Now with this logic, if it is 1 here, I will just use another color. Now it is 1 here, this will be plus 4. Now here it is already plus 6, that is within coil. This is plus 6. But for this next phase, this is for Y phase, it is 1 plus 4. It should start from 5. And then again it is next slot, because under each pole we will have 2 coils. So it will start from 6. Now again, similar for B phase. If it is starting from 5 and Y and B are displaced with 120 degrees, and 120 degrees means in terms of slots, it is 4 slots. So if it is 5, it is plus 4. It should start from 9. Can someone tell me what is this end in Y phase first coil? If it is 5, what is this number? What is the slot?
Yeah, 11 dash and 12 dash.
Exactly. So this is 11 dash and this is 12 dash. Because I already told you this coil span never changes in any winding. This is again 6 and this is again 6. And this is 9 and this will be 10 and this is again 6. Now this is again 6. Here comes a small logic. So 9 plus 6 is 15, right? Now,
That is
but
3 dash, sir.
exactly, because we don't have 15 slots. If you see this diagram, uh, these are the total number of slots, 12 only. After that, the 1 will start. After that, 2 will start. It's a round. After all, it's a machine. So it is 13, it is 14, it is 15. In convention, numbers we will get this. But what exactly is 15 slot? It is 15 minus 12. It is 3. As Ranjit said, if it is 15, we have to subtract it from 12 and we will get 3 dash. So what will be the number for this one? 10? It's 16. It means it is
4 dash.
4 dash. So yeah, this is how we completed the all coils under the north pole in all 3 phases. Now what should be the next coil in next south pole? So before going that, I want to tell, let's say we know that total coils are 12 coils, that is number of slots is equals to coils in double layer winding, and each phase R, Y, B, each phase will have 4 coils. We have seen here 4 4 4. Here also we will have another 2 coils in B phase. Now each phase will have 4 coils. Now in each phase 2 coils are under north pole and 2 coils are under south pole. Now let's look at what should be this number. What should be the number? Let's take R phase here first. uh, this is 1 7 dash, then this is 2 and 8 dash. So these are under north pole. Now coming under south pole, What is this number? Now we know that next two coils we are placing under south pole, and the coil span will be 180 degrees. Now if you see here, the south pole will start after 6 slots. The 6 slot is nothing but full pitch coil 180 degree, and the next pole will start from 7th one, that is total 180 degrees by each pole will swept. Now if I put a first coil here, uh, the second return coil, the starting of the south pole will have 180 degree displacement. Now how much is 180 degrees? How many slots is 180? We know that 180 degrees means 6 slots. So 6 slots, 1 plus 6, it will start from 7th slot. So we will see from diagram clearly. Now if it's double layer winding, 1 I have placed in 7, what is 7 dash, and the second one will start from here 7, and then it will go till 13 means 1 slot, and it will come back from here only, and it will like this, it will have a 1 dash. Now it is 7, and it will be the displacement will be 7 plus 6 now. Here the coil span is 7 plus 6 is 13, and it will be 1 dash, and subsequently the next will start from 8, and it will be 2 dash. So can someone tell me what is the number for this now? In Y phase, the starting coil under the south pole,
11 15 dash,
11,
11 5 dash.
11, correct, and it is plus 6, it is 7, it is 5 dash, exactly. And the second one is, if I start with 12, 12 slot,
6 dash.
6 dash, yes. Now similarly you can also complete for the B phase. So it's simple. So it all comes down to the logic and also the numbers. Uh, how good you are with the number logics, and it will come down to only the logics. You have to just understand everything. How many slot pole combinations? What is my slot pitch? What is my coil span? And from where I'm starting the each coil. If we know that, it becomes very easy to calculate this. Now let's get to our problem. So why the reason behind discussing all these concepts and solving numerical before going to a question is, you have to solve some basic questions before going to this kind of. Now if you see this question, here we are having how many slots? By looking at the diagram, we can see there are 48 slots are there. 48 slots, 3 phase. So before going that, okay, before going that, it is important to understand from the small problems, and you can solve these kind of big questions very easily. Now, so let's get into this question. I'm sure you will solve these questions very easily. Now, looking at the figure, can can anyone the question here, it is in the question it was given, it's a four pole machine. Okay, it was given as a four pole machine in the question. We can also see from here poles, sets of let's say it's north, it's south. If it is north, if it is south, it's also given in the question. Now, looking at the diagram, how many phases are there? Can anyone tell me number of phases? Yeah,
3.
yeah, it's a three phase machine. And how many slots are there? Slots are nothing but the
48.
maximum number, exactly. So here we have we can see the 48 is the maximum number here. So from that we have to calculate that there are total number of slots 48. So it's a double layer winding. How do I come to so is it a single layer or double layer? Can anyone tell me? Is it a single layer or double layer?
Double layer.
Double layer.
It is double layer. How can you justify it?
Mm, 11 is repeated. 11 slot.
Because of dash and 15, sir.
Yeah, both Venkatesh and Rajit both are correct. So if you are seeing some kind of dash and the same number is repeating again, it means that within that single slot we have two coil sides. So that is the indication that it is a double layer winding. Now we already discussed in a double layer winding, number of slots is equals to number of coils. Now, okay, coils per phase. Number of coils is 48 and my phase is 3 phase. So it from the diagram, let me get back to the red again. Okay. From the calculations we got that for each phase there should be 16 coils. So let's check from the diagram. Is it satisfying or not? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it is true. Number of coils per phase should be 16. That is validated from the diagram as well. Now, then, now this is very important question. Is it short pitched or full pitched? How will you find it? It's it's a very simple logic, but you have to put your mind. A simple logic you can say if it is a full pitched or short pitched.
Sir, full pitched.
Why it is full pitched? How did
Because electrical degree is 180 degree.
Okay, 180-degree should be the coil span in full pitched. So here, what is the coil span?
Well, span is 6. 6.
How it is 6?
Sorry,
10.
sir.
Yeah, here the coil span is 10 slots. So if it is 10 slots, one second. So yeah, 10 is correct. You are getting closer. So it is 10 slots. Now 10 slots is full pitch kind of finding or short pitch kind of finding. Okay, let's look into this way. If it is a full pitched coil, the coil span should be 180-degree, right? Now, how many slots accounts to 180-degree and what is the beta? Now, whenever you want to find whether it's a short pitched or full pitched, you calculate beta. Okay. Now, let's say let's say it's full pitch coil. For example, if it is a full pitched coil, my coil span is 180. That's for sure. In a full pitched, my coil span should be 180. Now, what is my slots per pole combination? Slots per pole is 48 by 4 is equals to 12. Now, to calculate beta, I need to calculate 180 by 12. So, in terms of electrical, I am calculating. Can anyone tell me what is 180 by 12?
15.
Yeah. So, it means that beta is equals to 15. The angle between each slot is 15 degrees. That means it is 15 degree slot pitch. That is what you get beta electrical. Uh, Now, if it is 15-degree, uh, it is 12 slots. If I start 1 here, my ending point should be plus 12. It should end at 13 dash. But where is my coil ending? Here the coil span is not 12 slots. Here the coil span is 10 slots. So as you said, the coil span is 10, but it also says that my winding is short pitched. Now, can you tell me if it is 111 dash as we see in the diagram, it is 10 slots. Now, what is my coil span here? Total coil span spread. Here it is 12 into 15 degree. It is 180 degree. But here it is 10 into 15 degree. Here my coil span is 150 degree. It is not 180. My winding is short pitched by how many degrees here? Epsilon is how much? 30 degrees short pitched because my coil span only spreading till 150. How I found it is 150 because if I my coil is a full pitched coil, if I placed my one side in slot number 1, the return path should be in 13th slot. But here my return path is in 11th slot only. So I found out from that relation my coil is a short pitched coil, and you can find what is the angle by which your winding is short pitched. And let's say let's calculate some more. Okay, it's already here. Maybe we can duplicate it. Yeah. So yeah, we found that our coil is short pitched and coils per pole. So my machine is a 4 pole machine and I have 48 coils and coils per pole is 12. Now if you also check from the diagram per pole, I have a 4 pole machine, right? So see, this one is north pole, this one is south pole, and this one will be again north pole, and this one will be south pole. These are the 4 poles. Now how many coils are under each pole? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. That is also matching. This is all we want to first inferences from the winding diagram they have given. Now, whatever data we can calculate from the diagram, whatever data we can calculate from the information given, that that solves half of the problem already. If you see the questions they are asking later, it will be already solved if we do this kind of analysis now. Now let's see the starting of B phase. See here. Uh, Now A phase is starting from 111 dash. Now what will be the starting of B phase? Don't look at the diagram, but let's say we want to find what is the starting of the B phase. So how to find that? I just told you the logic. So A phase, B phase, and C phase will be displaced by 120 degree. Now how many slots confined to 120 degree? Now that will come by 120 by beta. How much is beta? It is 15, right? So how much is 120 by 15? It's 8. So if I place a coil number 1 in A phase, this is A phase, I will have to place my coil that is in B phase, which is starting from 9, 9 slot. So is it matching from the diagram? It is matching. So yeah, what is the coil span? Coil span will always be same. It's 10. It's 19 dash. Now what will be by C phase starting? Now if it is like that, again it will be 8. 9 plus 8. The my C phase. It will be 17, and this span will be 10. Again 27 dash. So yeah, that is another standard basic concept behind finding out what will be the starting coil slot number in each phase. So that is also everything is clear now. Now let's go into the questions. Coil span, we already solved it. What is the coil span we got? How much is the coil span?
15.
No, no, that is beta. That is slot pitch.
Okay. 150.
Yeah, exactly. Our coil span is 150 degree. If you want to calculate it, so yeah, beta slot pitch is 15 degree. That we got, and our coil span will be, it is 1 and 11 dash, right? It is 10 slots, 10 into 15 degree. This is the procedure to calculate the coil span. You have to find the coil span in terms of slots first, and you have to multiply the slots with the slot pitch. So how did you calculate the beta? From beta you got from the total slots per pole, 180 by slots per pole. That way you will get the beta 15 degree. Using the beta you can calculate the coil span. Okay, pitch factor for third harmonic. So this is very important. Now, what is the formula for Kp? Do you remember the formula for Kp we have discussed? Cos epsilon by 2. Now it is K3P. We already talked about the reason behind short pitching the coil is to eliminate some kind of harmonics. Here we want to eliminate third harmonic. Now my epsilon will be 3 epsilon by 2. Okay. What is my short pitch angle? You remember? Uh, Coil span is 150. Total spread is 180. My epsilon is 30. 3 into 30 by 2. So how much is K3P? Cos 45. 1 by root 2. It's 0.707. So that's the pitch factor. It's simple. Now, yeah, phase spread. Now, phase spread is how much angle my each phase is spreading. That is what we are interested in. Now, before finding that, we need to find how many slots does my each phase is occupying. Now, then, if I know, if I want to see, if I want to coil span, I want to calculate how many slots my each coil is spanning. That we have to multiply it with beta, then we will get the coil span. Now, here we are trying to calculate phase spread. Now, before that, you calculate how many slots per pole by each phase is taking. So that will give you some number. That will give you some number of slots. So then you will get phase spread in terms of degrees. Now, slots per pole. How much is slots per pole? 48 per pole. This is 12. And now, in this, how many slots each phase is taking? Slots per pole per phase, 12 by 3, it's 4. Now 4 is the number of slots my phase is spreading. Now if you want to calculate in terms of angle, each slot confined to 15 degree slot pitch. Beta is always 15 degree. It's angle between, electrical angle between each slot. Now 4 slots contribute to 60 degrees. It's simple. So 4 slots, each phase is spreading. That means 60 degrees my each phase is spreading. Okay. Distribution factor. I'm sure you remember the distribution factor formula. That is sine m beta by 2 by m sine beta by 2. We already looked into detailed derivation of this today. Now here we are trying to eliminate third harmonic and K3D. Now sine m 3 beta by 2 m sine 3 beta by 2. Now m is nothing but the number of coils that are distributed. So to find this m, we need to find number of slots per phase we are placing. That is again the same number which we have calculated. So we want to find that number, and we need to see here it is third harmonic. So how number of coils that are distributed. So to find the number of coils that are distributed, we can also find that by slot per phase. Sorry, slots per pole per phase. This is nothing but the M here. 48 by 4 by 3. What is it number? 4. Now in the diagram, in the formula, M is equals to 4. And yeah, actually this is kth harmonic. K is equals to 3 and beta is equals to 15. With this, can you try to calculate the K3D? Sine 4 into 3 beta by 2 divided by 4 into sine 3 beta by 2. It's sine 60. This 2, sorry, 2, 30. Sine 90, 1 by 4 sine 45 by 2, 22.5. Can someone tell me what's the answer? 0.653. So this is the distribution factor for the third harmonic. So you also verify, it's a simple calculation and substitution only. Yeah, so we have to complete the remaining entries in the winding table, and we are interested in finding the values for x, y, and z. So you can easily complete all the windings now. See, okay. Now this is the starting coil in this south pole. If at all it is in north pole, and yeah, what will be the value of this particular number? And we already know there will be a eight slot distribution between starting of these two. Now 13 and this will be 21. And what is the x? It's simple now. If it is 21 in the top one, what will be the x now? It's 22. And the number here will be, can someone tell me what is the number here?
32.
Sorry?
32.
Yeah, right. Because it's a 10 span of here. So y we already calculated in the previous slide. So what is the y here? C is 17. Now if we get 17, we will get 18 here, 19 here, 20 here. And what is the z value here? So to find the z value, let's find the value here itself first. If it is 25, it will be 33. If it is 33, and this will be 43. And if it is 33, and what will be value of z here? 33 plus 8. It will be
41.
Yeah, it will be 41. Now you tell me what will be this number. By our logic, it should be 51. But
3.
yeah, it is 3 dash. For 51 minus 48. Okay, let's now find, sorry, w dash now. So to find w dash, let's go here. What will be this number? It is 37 plus 8. It is 45. Now what is w dash?
4.
No.
8.
No. Careful. Your calculation should be careful. It's simple subtraction and addition.
7, sir.
Yeah, it's 7. If it is 45, it should be 55. But there is no 55. The maximum is 48. Now 55 minus 48, how much it is? 7. It is 7 dash. So W is 7. In this way, it all comes down to number game, as I said. If you are good at logical reasoning, and it is very simple to solve this winding diagram. But don't make simple mistakes in calculations and additions. If you are good at this, and within 5 minutes you can solve all the winding diagram. How many slots it might be, even if it's 100 slot, 400 slots, it's come down to number game. You calculate the coil span, you calculate the number of slots per pole, and you find out what is your winding. Is it short pitched or full pitched? So you calculate all those numbers, and it will be very simple. Okay, so this is how we have found the values of XYZ, and you can always complete all the winding table present in that. So that's very easy. With the logic we have seen now, you can complete the entire now. Now we will see very few questions from the last weeks. We will see three questions from the last week. That is always related to our discussion today only. Week 3 and week 4, if you see it combined, they're very related topics. Now, you see here, 6 pole. Let's see the data. We have given a 6 pole machine, okay, 3 phase, 50 hertz frequency. It's a generator having a length of zero point 0.4 and the diameter of zero point 0.4 of that shoe or pole. And it's a 54 slot machine and 60 degrees phase spread. Even our old problem also having 60-degree phase spread only. And same double layer winding. And yeah, flux density is sinusoidal flux density with a peak magnitude we have given. So yeah, peak will be P max cos theta. That is the kind of flux distribution which is sinusoidal. Okay. Now the coil has having 4 turns. Turns is equal to 4 and short corded by 1 slot. So this is very important. Now whenever they talk about short pitched, this is the kind of information they give. We are short pitched our coil by 1 slot. It is short pitched by 15 degree. That kind of. Anytime you will be, we should be very comfortable converting slots to angle. Okay. Now we have to calculate slot pitch, beta in electrical degrees. Now how will you calculate beta? Beta is the basic for any kind of winding diagram. Beta is very important. Can someone tell me how to calculate beta? Number of slots is 54. How to calculate? Slots per pole is 54 by 6 pole. It is 9. Now beta will be 180 degrees by 9 is 20 degree. This should be very important. You should, by looking at the data itself, you should be able to calculate beta. And there is one more way to calculate beta. Like let's say this is a machine. You know it's 360 degrees, right? 360 degrees is divided by how many slots? 54 slots. Now how much is 360 by 54? It's 6.66 degrees, something like that. Now this is the mechanical beta. It means that there are 54 slots and 1 to 54 slots, and each slot is having a 6.66 mechanical degree. Now the question is beta electrical degree. Beta electrical will be mechanical into pole pairs. Now 6.666 multiplied by number of poles, 6 pole machine. Now if you multiply 6.66 into 3, you will get 20 degree. So there are two ways to calculate beta. In both ways you should get same answer. So yeah, this is very easy. Slot pitch and yeah, rated RPM. Now N is equals to very basic formula 120 F by P, right? What is the frequency given in the question? 58 frequency. Number of poles, 6 pole machine. So it is 1000 RPM. It's simple. And the last question for today is flux per pole in milliweber. It was asked. So we know that flux per pole is equals to B, sinusoidal distribution of B multiplied by area, because this will be in Weber per meter square and this will be meter square. Now there are two ways to calculate it, and if you know the maximum if it is sinusoidal flux distribution and if you know the peak B max, and your value of the RMS value of B max will be B max divided by pi by 2. 2 by pi of B max. And area, you know, pi dl, because you have given these parameters length and pi d. Pi d will be the cross sectional area of pole shoe, and it will be the length. So this is the pi d will be circumference and L will be the cross section. So this is one way to calculate that is B B max divided by pi by 2 multiplied by pi dl. This will give the flux. Then it should be per pole. So this is one way, and another way is if you know uh, there is a derivation you have to calculate through the what you call uh, you have to take the integral of flux density over the entire pole shoe. We have to pole area. If you take, you can also get the flux per pole in that one. I will just write the formula here. Flux per pole is equals to length into integral. It all depends on the distribution of that flux within because under every pole you will have same flux distribution. So if you take in electrical degree a total 180 electrical, each pole will be divided. So 180 by pole you will get the distribution, and you will try to integrate the sinusoidal flux density. It's a magnitude B peak and cos poles by 2 theta r, and it is multiplied by radius and the theta r. So even if you solve this integral, it will come down to this only. It's a shortcut to remember. Or let's see if you simply solve it now. Cos 1 integral you take and substitute the limits, and you will get 2 by poles multiplied by 2 b peak L into R. So this one, this is 2 times of radius. It is nothing but the d, right? That's diameter. Now the final formula will be 2 by poles b peak length into diameter. 2 by pole b peak LD. If you see here, pi will get cancelled in this formula. 2 b max dl by pole. So 2 b max dl by pole. Same thing. Even if you remember this, or if you go from derivation, you will get the same thing. And let's substitute now. 2 by number of poles. It's a 6 pole machine. And b peak, what is the b peak they have given? The question. It's 0.8 Tesla, and L and D are 0.4, 0.4. 0.8, 0.4 and zero point 0.4. Now can someone tell me what's the value of this? 2 into 0.8, 0.4, 0.46. It's 0.0426. It's what, flux, right? Weber per pole. But the question was asked in milliweber. So the question, if you see, it's in milliweber. So the answer will be 42.67 milliweber per pole you will get. So, sorry. Okay, where is that? Yeah, so 42.67 milliweber. So these are some of the questions from the week 3 content, and we are already end of the lecture now. The time is up now. So the concepts which I have missed now, and also some of the week 4 content, will be discussed with you in the next coming session, 7 to 9 session. Please do attend it, and you will get a understanding of all the concepts that are covered in this week. So I will just give a quick summary of what we have discussed today, and we have started with basic understanding of terminology in a machine. What kind of factors, what kind of terminology we are going to use in a basic machine construction. So we have started with distribution factor, and we see the detailed derivation on how to arrive at the distribution factor, and then we discuss the pitch factor and how to arrive at the pitch factor derivation. We also see that, and what is the importance of this distribution and pitch factor. That is very important. So why do we go for distributed winding and why do we go for short pitched winding? So that we have seen, and this combination winding factor we have seen it, and then we have started discussing the three phase winding. First we saw for a single layer winding, and then we saw the double layer winding from it, and we have seen basic winding diagram for a 12 slot 2 pole machine. With this, we started our today's week for discussion, where it is a 48 slot 4 pole machine 3 phase winding diagram, and you only solved all the problems. You yourself gave me the answers, and everything was. I hope it is everything is clear now. And with that, then we also solved week three discussion. Week three content we also discussed what is coil span, what is distribution factor, what is these are questions from the week four only, and this week three is also if you're given with a machine and this kind of data, what is the slot pitch, what is the rated speed, and what is flux per pole. So yeah, with this we covered both week three and week four, and I hope now we have covered the gap since the last 2 weeks. We apologize for the mismatch. So every time you are submitting the assignment before even the discussion happens. So from this week that won't happen, and from the next week we will discuss week five content, and so on. We will proceed. And if you have any doubts, please do ask me. Yeah, thank you, Ranjit. So yeah, thanks again for listening and attending the 2 hour session and listening to me patiently and answering along with me. That way, the interaction will be there, and that's a very healthy way of discussing the concepts. So, with this, if you have no doubts for today, please do attend the next session, and we will meet again in this next week, same time. Thank you all.